Well, as you can see from the title, you'll probably get a good idea of what I'll be talking about. Before we see some of the initial results of this study, let me briefly talk a little bit about the motivation behind it, or why we want to evaluate reanalysis datasets for simulating floods. And if we're trying to reproduce a long-term history of flood events and their characteristics globally, we can look at observational datasets, such as the ones from the Dartmouth Flood Observatory. And although that's a fantastic resource, it has limitations because it's based on satellite data, and in terms of record length, it can only go back to the satellite era. Alternatively, we can turn to models. And as we saw in Paul's talk before, we're at a point where we can simulate flooding over very large areas at fine enough resolutions on the order of a kilometer that will allow us to resolve specific flood events. So in order to test this modeling system, we decided to pick Australia, and specifically the Murray-Darling River Basin. Just keep pushing, okay. Well, in the box in the southeast corner of the map there, that drains about 1.2 million square kilometers. So it's very large to be able to run a hydrodynamic model with it. But as we're going to see in the next slide, a hydrodynamic model, which in this case is the LISFLOOD-FP model that uses a subgrid formulation for the channel. So although the grid cell is about a kilometer, it's able to simulate a channel that's narrower than that. And it requires inputs such as boundary inflows, and those are coming from a hydrology model, which in this case is the Variable Infiltration Capacity model, very widely used globally. And here's where the reanalysis data sets are coming in, because they need to force the hydrology model. And the minimum forcings that this particular model requires are precipitation, minimum maximum temperature, and wind speed. And these are all we can get from a reanalysis data set, which will allow us to go back 40, 50, even 100 years and be able to analyze a climatology of flood events, which will then allow us to do things such as identify trends or quantify changes with respect to precipitation, land use, and so forth. So one of the issues is that reanalysis data sets are rather coarse. So they're between 1 and 2 degrees spatial resolution. So we need to have a downscaling procedure in place. And for this study, we use 4 reanalysis data sets. You see them up there: NCEP, MERRA, JRA, and ERA analysis. So they're coming from NCAR, NASA, Japan, and then the ECMWF one. So what we did is we downscaled the rainfall fields down to 25 kilometers using a constructed analogs approach based on TRIM. So here you can see the schematic. I'm not going to go into too many details, but the idea is that you have a predictor for your rainfall fields, and you look into your past climatology to identify analogs to the coarse scale field that you're looking at. And then you pair up the coarse and fine scale, and with those, you can essentially use the same regression. You use linear combinations of those and use the same regression coefficients from the coarse scale to the fine scale, finally ending with 25-kilometer rainfall fields. For temperature, we just use bilinear interpolation, but taking into account the elevation, so we're using a lapse rate adjustment. And just for a sanity check, what we did is we took TRIM from 25 kilometers, aggregated it up to 2 degrees, and then applied this procedure. And here in the map here, you can see the coefficient of variation spatially for each month over the entire Australia. So basically, you can see the baseline, which is the TRIM in blue, and the downscaled fields with this approach. And you see that the match is really, really good, kind of giving some confidence that the method actually works. So here's some maps of the average seasonal accumulated rainfall over all Australia for the different data sets from reanalysis and TRIM. And Overall, you can see that the large-scale features are captured by all the reanalysis data sets. There are some differences, of course, between them, but we can see that in terms of magnitude and where the precipitation should be, we're doing a decent job. Now, although we capture the large-scale features, when we look locally, there are some differences, and we'll see that they have an impact later on when we're trying to simulate flooding. A little bit about the calibration of both hydrology and the hydrodynamic model. We calibrated VIC with a set of stations that are called hydrologic reference stations, so they try to minimize any regulation effects. The problem is that they have a small drainage area. There's an animation there that kind of shows you the time series of observed and modeled discharge. Observed is the purple color and blue is the modeled. Overall, we're doing a good job of capturing at least the peaks, but there are some issues in some of the stations, mostly because of the resolution discrepancy and because there's small drainage areas. There's also a global calibration available for VIC, but we decided to use this one because it yielded better results. At the bottom there, you can see the results from the calibration of the LISFLOOD model against a Landsat-derived inundation image and a water stage measurement. So here you can see an actual image of the water depths. And the RMSE and the bias were less than a meter overall, which is about the accuracy of the actual DM that we used, which is SRTM in this case. So looking at the results, at the top here you can see the channel volume from the benchmark LISFLOOD run, which uses the gauged inflows, which is the black line, through time. This is the seasonal volumes in the channel. And on the bottom you can see the floodplain volume. So again, the black color is the benchmark run. And then with the blue ribbon in both these plots shows the min and max of the reanalysis run. And the first thing you'll notice is that during the 70s, when we did have a very large flood event in Australia, we're not capturing that at all. And you can see that in the bottom plot. And as we move through time, you can see that we're doing a better job in the channel volumes, but there's still some discrepancies. As you can see, for example, there's a discrepancy, sorry about the pointer, but anyway, there's a discrepancy in the 90s, and as we move further, there's a larger flood event that the reanalysis predicts in 2007 and 2008. No. Never mind. Anyway, but at least in terms of the channel volume, we are capturing the recent floods in 2011 and 2012. However, again, we see that we have a major issue with capturing the floodplain volume. And there's an argument to be made about recalibrating the hydrodynamic model, because bathymetry in LISFLOOD is calibrated with the gauged flows. If we tried calibrating against the reanalysis flows, then we might get a better picture here. However, the difference is very large for it to be just attributed to the recalibration issue. And then if we're going to trust one of the calibrations, we're probably going to trust the one against the gauge flows. Here we're looking at similar plots, but on the top we have the total inflow into the system. The blue solid line is against the gauged inflow. Lighter blue is the ensemble of the reanalysis, and on the bottom we have, again, solid color is the baseline coastal outflow, and the lighter red is the reanalysis one. So again, you can sort of see the same results. In the 70s, the gauged inflows are much higher than what reanalysis says. In the 2007-2008, we have much higher flows coming into the system, but if we notice closely, we can see that, for example, in the places where we're not, in the times when we're not doing so well before, we seem to be sort of capturing, at least the ensemble is kind of containing the gauged inflows. So that suggests that we not only have a problem of how much inflow we have, but where. So we have the inflow in different places than we should be, in the wrong places. So even though you're looking at the total inflow, we might think that we're doing okay. We're actually are not. And this becomes more obvious when we look at a flood inundation climatology, which essentially shows the frequency normalized from 0 to 1 of the pixels that are wet during the 40-year climatology that we have from 1973 to 2012. And on the left, you can see the benchmark run, so you can see a lot of flooding in the Darling, the Warrego on the north, and the Murrumbidgee and Mare in the south. When you look at the reanalysis, we're only doing relatively okay in the Darling, in the sort of the 30 degrees south, but the Warrego we're not capturing at all, and then the Murrumbidgee in the south we're not doing a good job at all. And that again reflects back to the plot that we show between the channel volumes and the floodplain volumes. So we just don't have enough water, and also the bathymetry is not at the place where it should be. So we could do a slightly better job, but this suggests that we're definitely having a problem with the volume of water coming into the system. So in a bit more detail, we're going to look at 3 stations. So this is the Darling station. On the top, you can see a time series of monthly rainfall, and in the bottom, you can see the resulting discharge in blue from the reanalysis, and red is the observed. So the first thing you'll notice immediately is that in the 70s, where we have the large flood event, we're not capturing in terms of the discharge, but also when we look at the precipitation, the magnitude of the precipitation is about the same in the other flood events, for example, in 2011 and 2012. Whereas, given the discharge time series, we would expect in the 70s to have much higher rainfall. Looking at a different station, the Warrego, again, we're significantly underestimating the discharge. And the same thing happens when we look at the Murrumbidgee, and that basically reaffirms what we saw in the previous plot. So what we wanted also to do is try to use a very, very simple approach that what it does essentially is it makes a number of assumptions and assumes, for example, that the discharge is a result of storage in the basin, and by selecting by selecting a subset of the time series of observed discharge, we can fit a function, the GQ, which represents the sensitivity of discharge to storage, and then from that we can do hydrology backwards, in a sense, infer the precipitation that should have fallen to produce the observed discharge. So nothing's calibrated here, we're just using the observed discharge, and in the bottom you can see an example of that inference where at the top we have the observed discharge for 1 year daily, and at the bottom we have the rainfall that should have produced that discharge. So you can sort of see that the time series agree, and again, this is very crude, very simplistic, but it gives us an idea of at least how much precipitation should we expect. So this plot here shows the station in Murrumbidgee. In the green, you see the NCEP, and the results are the same for the outer reanalysis data sets. And the blue is the inferred precipitation. So again, with no model involved here, just using the discharge time series, we can see that we're significantly underestimating the rainfall that gets into the system and then is being fed into the hydrodynamic model. So I'm almost out of time, so I'll just finish with a quick laundry list of things that we want to do to keep exploring this. And the first thing is trying to look at monthly data sets, for example, the CRU, to try to correct the reanalysis. It would be good to quantify what the impact of recalibrating the hydrodynamic model is, although I think we should try to keep the calibration with observed data. There's some potential issues with flow regulation. Then we can see whether we can reproduce some of the correlations we see with climate signals like ENSO, the Indian dipole, and then also look at the practical implementation, because if we're going to take this global, it would be good to automate a lot of these steps of calibration and downscaling, so we would be able to just produce this without a lot of manual tweaking. And I'll finish with that. Thank you.
Questions? Hi, Bob.
Could you check your inferred precipitation against ground gauge?
Yeah, we could. I mean, that's one of the things we want to do. It can be a bit tricky, again, because it has to be a specific type of catchment where, you know, only storage is affecting discharge, but we could definitely just pick certain catchments and do that. So that's part of the next steps. So they're not handled in the hydrologic model. So essentially, that's one of the things we want to look at, is to see how much of an impact the flow regulation has in capturing those really large flood events. So that's actually part of a project that we have where we're going to build a component into VIC that handles dams, irrigations, diversions, and so forth.